Somewhere in the constellation Camelopardalis, a faint, unremarkable red dwarf star sits 25 light-years from Earth, close enough on a galactic scale to be considered part of our own cosmic neighborhood. For nearly 2 years, astronomers believed they understood the planet orbiting it reasonably well. They had its mass, they had its orbital period. They'd filed it away as a mini-Neptune, a larger gas-dominated world, interesting enough for the catalog, but not exactly a priority target in the ongoing search for potentially habitable worlds. Then, in the summer of 2026, a team of American astronomers went back and looked again, using better instruments and a more careful analysis, and the numbers that came back completely rewrote what this planet actually is. This is the real story of GJ3378b, how a routine data correction turned an overlooked planet into one of the most exciting nearby habitable zone candidates astronomers have ever identified. And why, even with the James Webb Space Telescope, currently the most powerful tool humanity has for studying distant atmospheres, this particular world remains just out of its reach. I'm your host, and this is your channel. If you want the real science behind the search for other worlds, subscribe now, because we're just getting started. Let's start with why this story matters at all, because understanding the broader context of how astronomers currently search for habitable worlds makes the specific correction at the center of this discovery so much more significant. As of 2026, scientists have confirmed nearly 6,000 exoplanets orbiting stars beyond our own sun, and the vast majority of them were found using one of two primary indirect detection methods. The transit method watches for the periodic, tiny dimming of a star's light that happens when a planet passes directly in front of it from our specific vantage point on Earth. The radial velocity method, the technique responsible for identifying GJ3378b in the first place, instead measures the subtle gravitational wobble a planet induces in its host star as the two objects orbit their shared center of mass, detected as a tiny, measurable shift in the wavelength of the star's light. Both methods have their own genuine strengths and limitations, and understanding those limitations is essential to understanding exactly why this planet needed to be re-examined at all. Radial velocity measurements are particularly useful for finding planets around nearby, relatively bright stars, but calculating a planet's true mass from this data alone carries an inherent complication. Without knowing the exact tilt of a planet's orbital plane relative to our line of sight, which typically requires the planet to transit its star to determine directly, any mass estimate calculated purely from radial velocity. Data represents, at minimum, a reasonable estimate rather than a fully certain figure. Get that orbital geometry slightly wrong, and your entire mass calculation, along with everything scientists infer about the planet's fundamental nature, shifts along with it. That's essentially what happened with GJ3378b. The planet was first identified back in 2024 by a team of French astronomers using the Canada-France-Hawaii telescope on Mauna Kea, and their initial radial velocity data indicated a planetary mass of roughly 5.25 times that of Earth, a figure that placed the world firmly in what astronomers call mini-Neptune territory, a larger planet likely dominated by a thick atmosphere of gas rather than a solid, rocky surface. For roughly 2 years, that was the working understanding of what GJ3378b actually was. In 2026, a research team led by Paul Robertson at the University of California, Irvine, went back and re-examined the planet using two different telescopes, including the WBAW-WIN-3, 5-meter telescope at Kitt Peak National Observatory in Arizona, gathering additional, more refined radial velocity measurements. The results significantly overturned the earlier picture. Robertson's team calculated the planet's true mass at roughly 2.3 times that of Earth, dramatically smaller than the original figure, and squarely within the range astronomers classify as a rocky super-Earth rather than a gas-dominated world. At the same time, the team also revised the planet's orbital period, correcting it from the originally measured 25 days down to 21 days, meaning GJ3378b actually orbits its faint host star noticeably closer than anyone had previously realized. Here's why that specific combination of corrections turned out to matter so much. Because GJ3378b's host star is a cool, dim red dwarf, dramatically fainter than our own sun, a closer orbital distance doesn't automatically translate into an inhospitably hot planet the way it would around a sun-like star. Instead, the revised orbital distance places GJ3378b comfortably inside its star's habitable zone, the specific range of distances where surface conditions could theoretically support liquid water, assuming the planet retains an atmosphere capable of maintaining adequate temperature and pressure. Robertson quantified precisely how favorable that positioning actually is, noting that GJ3378b receives approximately 90% of the stellar radiation Earth receives from our own sun, a genuinely close match that he described plainly as putting the planet right in the sweet spot. Reacting to the overall significance of the corrected findings, Robertson didn't hesitate. This one, he said, is exciting, adding that at 25 light-years away, GJ 3378b counts as one of our closest cosmic neighbors, genuinely nearby when measured against the roughly 100,000 light-year breadth of the entire Milky Way galaxy. Now here's where honesty about the current limits of our knowledge becomes essential, because this is exactly the point in the story where exaggerated headlines tend to run ahead of the actual science. Robertson's own team has been explicit and direct about this. All we currently know for certain about GJ 3378b, based on radial velocity data alone, is its mass and its orbital period. We genuinely do not know whether the planet has any atmosphere at all. We don't know its surface composition, its actual temperature, or whether it bears any resemblance to Earth in terms of oceans, continents, or weather patterns. It's entirely possible that GJ 3378b has land and sea and clouds. It's equally possible that it's a completely airless, cratered rock, stripped bare by relentless stellar radiation, with nothing remotely habitable about its actual surface. Based on what astronomers currently know, there is genuinely no way to distinguish between those two dramatically different scenarios. This is precisely where the James Webb Space Telescope enters this story, and it's important to be accurate about exactly what role it can and cannot currently play here. Webb has become the single most powerful tool available to astronomers for studying the atmospheres of distant rocky exoplanets using a technique called transit spectroscopy, which requires a planet to pass directly in front of its host star from our specific line of sight. As that transit occurs, a small fraction of the star's light passes directly through the planet's atmosphere before continuing on toward our telescopes, and different atmospheric gases absorb very specific, identifiable wavelengths of that light in the process, leaving a detectable chemical fingerprint. This is exactly the method Webb has used to detect molecules like methane, carbon dioxide, and water vapor in the atmospheres of other rocky, potentially habitable exoplanets, including several planets within the well-studied TRAPPIST-1 system, roughly 40 light-years from Earth. But GJ 3378b does not transit its star from Earth's vantage point. Its orbit simply isn't tilted the right way relative to our line of sight, meaning none of its host star's light ever passes through its atmosphere on the way to our telescopes. There's no transit signal at all for Webb, or any other current instrument relying on this technique, to actually analyze. This isn't a shortcoming of Webb's technology. Webb remains, by a substantial margin, the most sensitive infrared observatory ever built. It's simply a matter of orbital geometry, an accident of how this particular planet happens to be positioned relative. To us, that puts it beyond the reach of the one technique currently capable of revealing anything about its atmosphere. According to Robertson's team, meaningfully answering whether GJ 3378b actually has an atmosphere at all will most likely have to wait until the 2040s, when NASA's proposed Habitable Worlds Observatory, a future telescope specifically designed around direct imaging of potentially habitable worlds rather than transit spectroscopy, is expected to launch, opening up an entirely different observational pathway that doesn't depend on a planet's orbital alignment at all. Despite that real, honestly acknowledged limitation, the broader scientific community remains genuinely encouraged by what this discovery represents, and that optimism is grounded in something specific about GJ 3378b's particular circumstances. Michael Endel, an astronomer at the University of Texas at Austin who contributed to validating these findings, framed the stakes of this entire research effort clearly. The ultimate goal driving this whole field is the eventual detection of genuine biosignatures, direct chemical evidence of life on another world, answering with real, verifiable data. The question of whether humanity is truly alone in the universe. Endel described the current era of exoplanet research as still being fundamentally in what he calls the reconnaissance phase of our solar neighborhood, the patient, methodical process of simply identifying which nearby stars actually host planets in the first place, since those nearby worlds will always represent the easiest, most accessible targets for eventually detecting a genuine biosignature, given their relative proximity and brightness compared to more distant candidates scattered throughout the galaxy. GJ 3378b, in his words, brings us one step closer to knowing all of our neighbors, and ultimately, which of them might genuinely be hospitable to life. There's also a specific, scientifically grounded reason for real optimism buried in exactly where GJ 3378b sits, relative to one of the most serious threats facing planets orbiting red dwarf stars. Despite being the single most common type of star throughout our entire galaxy, red dwarfs come with a significant complication for long-term habitability. They tend to be considerably more magnetically active than stars like our own sun, particularly during their younger years. periodically unleashing intense stellar flares and powerful winds capable of gradually stripping away a planet's atmosphere over the course of millions or billions of years. A troubling pattern James Webb has already documented while studying multiple rocky worlds orbiting other red dwarfs, including several planets within the TRAPPIST-1 system. That pattern has meaningfully tempered some of the early optimism surrounding red dwarf planetary systems as promising places to search for habitable Earth-like conditions. GJ 3378b, however, according to Robertson's team, sits right at the edge of the zone where planets orbiting this particular category of star are expected to face the very worst of that radiation exposure, meaning there's a real, scientifically grounded possibility that it managed to escape the most severe atmospheric stripping, potentially retaining enough of an atmosphere to remain genuinely habitable or even support life, should the right underlying conditions have aligned. So here's where this actually stands, honestly, in the middle of 2026. A rocky, Earth-sized planet, one of the most promising nearby. Habitable zone candidates astronomers have identified in years, sitting just 25 light-years away, and receiving almost precisely the same amount of stellar energy that Earth receives from our own sun. A significant self-correcting revision to earlier data that transformed our understanding of this world from an unremarkable gas-dominated mini-Neptune into a genuine, credible candidate worth real scientific attention. And a currently unanswerable question, whether GJ 378b has any atmosphere at all, sitting just beyond the reach of even our most sophisticated current instruments, waiting for a future observatory, purpose-built for exactly this kind of challenge, to finally provide a real answer sometime in the 2040s. This is the honest, current state of one of the most compelling nearby exoplanets astronomers have ever identified. Published in the Astrophysical Journal on June 30th, 2026, representing exactly the kind of careful, patient assault, and yes, occasionally self-correcting science that will eventually tell us, whether that takes years or decades, whether we are truly alone in this universe. If this kind of story is what you come here for, one grounded in exactly what astronomers have actually found, and honestly don't yet know, hit subscribe and turn on notifications, because there's a lot more of our cosmic neighborhood left to map. Drop a comment telling me what you think future telescopes will eventually find on GJ 3378b, and share this with someone who still thinks we haven't identified any real candidates close to home.